Okay, so what this gives us then is that this tells us then that E at n plus 1 equals minus sum I going from 0 to n a to the power I delta t tau t at n minus I. Okay. All right. Let's work with this, and we're going to work now by invoking some inequalities. Okay. In particular, what we can say first of all is that the first step that we will take is not an inequality. It is to say that the magnitude of En plus 1, right, is equal to essentially magnitude of sum I going from 0 to n a to the power I delta t tau t n minus I. Okay, right, we're taking the magnitude of that sum, the absolute value of that sum. Now is where things get really interesting. Now is where the inequalities come up, okay? And remember, when we write the inequalities, I'm going to start out by writing this. And you recall when we looked at our error analysis for the finite element method, I made the point that when I write such an inequality, what I mean is that the previous right-hand side, this one, is bounded from above by what I'm about to write now as the new right-hand side. Okay, so what I get is that that is lesser than or equal to I going from 0 to n, the magnitude of the absolute value of each one of those terms, and that's a to the power I. A to the power I delta t tau at t n minus I. Okay? All right? The absolute value of a sum is bounded from above by the sum of the absolute values. And this result is a very standard step in analysis. It is called the triangle inequality. Okay, but there is more. We can say further that our most recent right-hand side itself is bounded from above by this expression. Okay? Essentially what we're saying here that is that that any absolute value, which is a product, right? So the absolute value of a product is bounded from above by the product of the absolute values, right? And this result is called the Cauchy-Schwarz inequality. Okay, but now we have more. We have stability, right? If our method is stable, what we're able to say is that sum I going from 0 to n of 1 times magnitude of delta t times tau t n minus I bounds from above our previous right-hand side. Okay? Essentially what I've done is replace AI with 1. Right? And why am I able to do that? It's a property of the methods we're looking at. What property are we applying here? It's stability, right? Because we know that the magnitude of A has to be lesser than or equal to 1 the absolute value of a has to be lesser than or equal to 1 for stability. Therefore, a to the power I has an absolute value also lesser than or equal to 1. Okay, so if we substitute that with 1, we get a bounding from above of what we had as our previous right-hand side. Okay, but now the story goes on. Now we know the delta t is a positive quantity, right? So what we can do here is we know that delta t is a positive quantity, and furthermore we know that for tau the condition of consistency allowed us to say something about it. Okay, so in one step I'm going to do this. I'm going to pull the delta t out, all right, and I have inside my sum c delta t to the power k. Okay, why am I able to say this? It's because we said that we have consistency. Okay, right, we have consistency. Now one could introduce another step inside here, which would be to first say that, well, of all the taus over all the n minus i's, I take the maximum of them, okay, and then I get to this point, right? So let me say that one can say inside here, one may first, if one wanted to be really careful about this, and I guess one should be really careful, so one would say that first of all we would have a previous step inside here, which is to say that this right-hand side, right, using that, one could say that, sorry, the entire right-hand side, not just that. One could say that this entire right-hand side, first of all, would be bounded from above by sum I equals 0 to n delta t times the maximum over all I t n minus I. Right? One could take that step, right? Which is to say that, well, since each of the tau, you have a different value of tau for each time step, let's consider the maximum over all I. Okay? But then we know that that maximum has to be bounded from above by c delta t to the power k because we have consistency, right? So then we get to this step that I have here, right? Okay. All right. Okay. Now, well, what do we get here? We have delta t times, sorry, the sum here goes from 0 to n, sorry, right. Okay, we have delta t times a sum of n plus 1 steps, because I is going from 0 to n, of that quantity c delta t times c delta t to the power k. Okay, so we can very well say that it is just like multiplying delta t essentially n plus 1 times, right? So this thing is lesser than or equal to t to the power n plus 1, sorry, t at n plus 1, not t to the power n plus 1, but t at n plus 1 times c delta t to the power k. Okay? All right, just summing over those n plus 1 steps. Okay? Right? Right? Now, and now from here we see, however, we see that as delta t tends to 0, right, because k is greater than 0, right, then as delta t tends to 0, we see that the right-hand side also tends to 0. Okay? Right? But limit delta t tends to 0 of c delta t to the power k is equal to 0 for k greater than 0. Right? And where do we get this? Why are we allowed to say that k is greater than 0? Once again, it is the result of consistency. Okay, so what we see finally is that the absolute value of our modal coefficient of the error is bounded from above by essentially by 0, right? Which means that it itself tends to 0, right? In the limit, as delta t tends to 0, right? What we are seeing is that that quantity is less than or equal to 0. Okay, so indeed we have convergence, right? And that's the end of our proof. Okay, I'll make a quick remark here, which is that what we've seen here is a demonstration of the use of consistency and stability implies convergence. Okay, which is a very standard, it's actually a theorem in numerical analysis. Okay, it's called the Lax theorem. Okay, all right. We're actually done with this entire topic of methods for parabolic problems. And the approach we've taken, if you just to summarize, is to carry out our standard spatial discretization using the finite element method, but do the time discretization using finite difference methods. And since here we're looking at first order problems, we looked at the Euler family. We analyzed its stability, understood its the behavior of its higher order modes, looked at consistency, and looked at how stability and consistency give us convergence. Let me make one more remark now about the use of the different algorithms. Okay, in particular, let me do this. Okay, let me say that here I have alpha. Okay, and let's look at alpha equals 0, alpha equals 1/2, and alpha equals 1. Okay, and just for connection to other things, let's give these algorithms their names, right? So this is forward Euler. Right, this is the midpoint rule or the Crank-Nicholson method. And this is backward Euler. Okay, let's look here at the stability. Let's look at order of accuracy. And let's draw a straight line. Okay, better. And let's look finally at high order modes, right? Okay. Stability of forward Euler is conditional. Right, and we've seen the stability condition. Midpoint rule and backward Euler are unconditionally stable. Okay. Order of accuracy. Forward Euler has order of accuracy 1. Midpoint rule has order of accuracy 2. Backward Euler has order of accuracy 1. For high order modes, limit as lambda h delta t tends to infinity, limit of a in the, as lambda h delta t tends to infinity, not 0. Okay, forward Euler is, let me just say it tends to minus infinity, right? Because nothing can be equal to minus infinity, all right? Midpoint rule, limit lambda h delta t tends to infinity is equal to minus 1, okay, oscillatory behavior. For backward Euler, we see that limit lambda h delta t tends to infinity, sorry, limit of a here, okay, here too, limit of a equals 0. Okay, so it damps out high order modes, dissipates them away. So this is the, broadly speaking, the behavior of the three main, or the three most commonly used members of this family. Depending upon the problem, you choose your method. Okay, all right. We're done with this segment and with this unit here. When we return, we will take up the problem of elastodynamics.